The objective of this lab was to model a skydiver's fall from approximately 120,000 meters above the Earth's surface in order to find the exact moment at which the person would break the sound barrier. At the end of my lab, I found that the person would break the sound barrier at approximately 40 seconds. In order to correctly model this fall, we will need to use Newton's second law in order to calculate the velocity that the person is moving at, shown here. Part of the law will need to take into account the force of gravity in order to find the net force, and the force of gravity, unlike previous labs, is not just going to be 9.8 times the mass of the object, because the person is going to be so far away from the surface of the Earth that the pull of gravity will be slightly smaller, ranging from 9.6 to 9.8 depending on where the person is. The equation for finding little g is shown here. The only other force acting on the skydiver will be the drag force, which is proportional to the velocity of the diver and the air density from where it is in our atmosphere that he is falling from. In order to find this force, we will need to know the surface area being affected by the drag force, the drag coefficient, the density of the fluid, which in this case is the air, and the velocity of the object, which we will calculate using Newton's second law. And we will assume that at the start of the fall, the person's starting from rest, so the starting velocity is 0. As you see, in order to calculate the drag force, we will need to know the density of the fluid. And as you can see here, in order to know the density, we're going to need to know the air pressure of the air. And we can find the air pressure relative to how high up the skydiver is using this equation. Once we have pressure, the only other thing that we will need to find is this temperature specifically at where the diver is. Because we already know R. It's the same R we used to find the pressure. This picture shows how the temperature changes throughout our atmosphere at different heights. So if the slope of this line, of each of these line segments is known, since we know the starting temperature, we can find what temperature the air would likely be at based on where the skydiver is. This is the method I use for finding the temperature. We now have everything we need to find the density, which means we have everything we need to find the drag force. This graph shows what I came up with for the density of the air based on where you are in the atmosphere. As you can see, it is an exponential equation. Using this, I was able to model the fall, and I came up with this for the position data as far as height over time goes, which corresponds to this velocity over time graph. The speed of sound is approximately 340 meters per second, and as you can see by this, the velocity is at that speed at approximately 40 seconds.